Another lecture on partial differential equations. We solve partial differential equations using Fourier series, and in the previous lecture we have done that for the heat equation. Now we've also observed that if the data in the heat equation are constant, then over infinite time the solution of the heat equation asymptotically approaches a steady state. That steady state, on the other hand, solves another partial differential equation, which is known as the Poisson equation. In this lecture, we take a look at the Poisson equation as an interesting subject of study on its own. The Poisson equation can be motivated as follows. Suppose we've got a stationary heat distribution that does no longer change in time. That just means that for all x and for all times t, the time derivative of u equals 0. d over dt, u xt equals 0. Now, the stationary heat distribution, of course, still satisfies the heat equation. And since the time derivative in the heat equation vanishes, we can now simplify the heat equation. We are left with the following differential equation. Negative kappa of the second derivative in x of u in x equals f of x for all x in between 0 and L. And since the data are constant, we also have got constant boundary values. u0 equals some fixed value g0 and ul equals some fixed value gl. In that manner, we derive a differential equation that is a boundary value problem. And that boundary value problem is known as a Poisson problem. In the special case that f equals 0, we also call it the Laplace problem. As usual, we will discuss uniqueness of the solution before we discuss the existence of the solution. And the way we do that again is we assume that we've got two solutions, u1 and u2, and then we show that the difference between those two solutions must necessarily be 0. So if u1 and u2 both satisfy the Poisson equation with the same right-hand side f and the same boundary values, then let us write v as the difference of the two solutions, v equal u1 minus u2. We can then easily calculate that negative kappa of the second derivative of v equals 0 for all x between 0 and L. So we actually have got a Laplace problem. In the next step, we multiply this differential equation by v itself. So we get that negative kappa of v prime prime x times vx equals 0. And then we integrate both sides of the equation in x. So the left-hand side becomes negative kappa integral from 0 to L v prime prime x vx dx. And similar to before, we can perform an integration by parts. We roll over one derivative from v prime prime onto v and use that the function v vanishes at the boundary points. And so we get that this integral equals kappa, the integral from 0 to L, v prime x squared dx. However, from the previous equation, we already know that this integral has been 0 all along. Now, if the square of the first derivative of v has integral 0, that can only be true if the first derivative of v equals 0 everywhere. So we get that v prime equals 0. In particular, v must be constant, since its first derivative vanishes, arguably. But then we also know that v vanishes at the boundary points. For example, v of 0 equals 0. So not only is it constant, it must already be constant 0 everywhere. v equals 0 everywhere for all x between 0 and L. So the difference v vanishes. That is, the difference between u1 and u2 equals 0. And we conclude that u1 and u2 must have been the same all along. That shows the uniqueness of the solution to the Poisson problem. Having discussed the uniqueness, let's discuss the existence. And as before, we consider the special case where the boundary values equal 0. All this is very similar to the discussion of how to solve the heat equation via Fourier series, but this time there's no time variable. So let us assume that the source or sink term is represented by a Fourier series. f of x equals a f naught plus the infinite sum starting in n equal 1 going up to infinity of a f n times the cosine mode cosine 2 pi n x over L plus b f n times the sine mode sine 2 pi n x over L. That's how we represent the source term f, and we also represent the solution as a Fourier series. E of x equals a naught plus the infinite sum starting at n equal 1 going up to infinity of an cosine 2 pi n x over L plus bn sine of 2 pi n x over L. By the very same argument that we already used in the discussion of the heat equation, we only focus on a Fourier sine series. That means other coefficients a of n and an equal 0 for all indices n. Now let's suppose that we want to represent the solution as a Fourier series. In that case, since we deal with a partial differential equation, it makes sense to take a look at how can we represent the derivatives of u as a Fourier series. So let's take a look at the first and second derivatives of u and x. D over dx, u of x, equals the sum starting at n equal 1 going up to infinity of bn 2 pi n L 2 pi n over L times cosine 2 pi n x over L. That can be obtained just by applying the first derivative to every term, to every single term in the Fourier series. And so we can readily read off all the coefficients. Bn times 2 pi n over L. Next, from there we can already compute the Fourier sine series of the second derivative. If we take the second derivative of u and x, we see that this can be represented as the following series. We sum up starting at n equal 1 up to infinity. Bn times negative 4 pi square n square over L square times sine of 2 pi n x over L. In particular, the second derivative in x can again be represented by a Fourier sine series. Okay, having done that, let's see what we can find out about the coefficients Bn of the solution. What we can do is take both sides of the Poisson equation and integrate them against the Fourier frequencies, against the Fourier modes. If we do this for, let's say, the nth Fourier sine mode, we get the following. Negative kappa of the integral from 0 to L of the second derivative of u and x times the sine of 2 pi n x over L dx equals the integral from 0 to L of fxt times sine 2 pi n x over L dx. Now we know that the integrals on the left and the right hand side extract the coefficients of the corresponding Fourier series. The Fourier series of the second derivative of u and the Fourier series of f. Therefore we extract the following. On the left hand side we get a negative kappa times negative 4 pi square n square over L square bn equals bfn. That equals, corresponding to the right hand side, bfn. Now we can perform some very obvious simplifications and we get a closed formula for the coefficient bn. We just isolate bn on the left hand side. And that yields that bn equals L square divided by 4 kappa pi square n square multiplied by bfn. So in that case, extracting the coefficients of the original solution is very easy. We just take the coefficients of the Fourier series of f, the source term, and then multiply them by specific factors. Putting everything together, we get that the solution of the Poisson problem has got the following form. Ux equals the infinite sum starting at n equal 1 going up to infinity of L square divided by 4 kappa pi square n square times bfn multiplied with the nth Fourier sine mode, sine of 2 pi n x over L. So we can tell that if we know how to represent f in terms of a Fourier series, if we can do that, then the solution of the Poisson problem can be computed fairly easily just by multiplying the corresponding coefficients and then setting up the Fourier series of the solution. At this point, we can make one more observation. Namely, just let's take a look at the nth Fourier sine mode, the sine of 2 pi n x over L. If we take the negative of the second derivative in x of that Fourier mode, some simple computations tell us that this equals 4 pi square n square over L square times the sine of 2 pi n x over L. Now, people have observed this identity, and to mathematicians, it looks very similar to the relation of eigenvectors and eigenvalues that you might know from linear algebra. we apply an operation to the nth Fourier sine mode, sine 2 pi nx over L, and again we get the same Fourier sine mode multiplied by some constant. And that is a reason why we use the notion of eigenfunction and eigenvalue in that context. We call the sine of 2 pi nx over L an eigenfunction of the Laplacian negative second derivative in x, corresponding to the eigenvalue for pi square n square over L square. In that manner, solving the Poisson problem reduces to multiplying the coefficients in the Fourier series just by the corresponding eigenvalues. That's precisely what we've done on the previous slide. We take the nth Fourier coefficient of the right-hand side f and divide it by the nth eigenvalue of the Laplacian. That gives the solution. Finally, let's remember that the Poisson problem can be derived as a steady-state solution of the heat equation, asymptotically as the time goes to infinity. So let's see whether we can recreate this from the solution formula for the heat equation. We had that the Fourier coefficients of the solution of the heat equation have the following formula. The nth Fourier coefficient, Bn, depending on time, can be written as B0n times the exponential of negative 4 times kappa pi square n square divided by L square times t. That is the term influenced by the initial values, plus Bfn multiplied with the integral from 0 to t of the exponential of negative 4 kappa pi square n square divided by L square multiplied by s minus t ds. Now what happens as time goes to infinity? On the one hand, we observe that the very first term corresponding to the initial conditions goes to 0. That's because we have got this negative exponential. As t grows larger and larger, this negative exponential goes to 0. So what about the second term? We can take a look at this as follows. Let us abbreviate a equal 4 kappa pi square n square divided by L square. The last integral can then be abbreviated as the integral from 0 to t of the exponential of negative a times s minus t ds. And so to simplify the discussion even further, we make a substitution of variables and write this as the integral from 0 to t of the exponential of negative as ds. Now what happens as t goes to infinity? Then we have the integral from 0 to infinity of the exponential of negative as ds. And that's something we can compute. That integral equals negative 1 over a times the integral from 0 to infinity of negative a times exponential of negative as ds. So I multiply by minus a and divide by minus a. And now the fundamental theorem of calculus gives the following result, 1 over a. Now what does it mean? That means that in the limit as t goes to infinity, the nth Fourier coefficient of the solution approaches Bfn multiplied by 1 over a. But that's just exactly the solution formula we have seen previously for the Laplace equation. So the solution formula for the Laplace equation is recreated here by taking a look at the limit of the heat equation as the time goes to infinity. I think that's a pretty neat result which rounds up the theory quite well. Now in the next lecture we take a look at something vastly different, namely the wave equation.